Inductors.
Inductors, yeah. So, how do you draw an inductor? Like this?
Yes.
Is that your favorite symbol?
Yeah. No, my favorite symbol is a resistor.
No, favorite symbol for an inductor.
Yeah.
Why the favorite symbol of a resistor?
Because it's the easiest thing to deal with.
Okay, well, not always. Now, again, everything is basically the same. We just have to change something, but the principles are basically the same that we used for the capacitor. Well, actually, we can do something like that. I just give you some hints, and then you are making all this part by yourself.
Okay.
Okay. Now, we have a current, again. Let's say that you have a solenoid.
Yeah.
And it will create, you inject some current. It will create a magnetic field. And you know that the magnetic field, then it will have a magnetic field, a magnetic flux density B, which is
Mu.
Mu times H. Okay, and the flux is B times the surface, okay? So if you have a surface and there is some B, B in fact is the magnetic flux density. So
Yes.
B is the magnetic flux density.
What's H? Magnetic flux.
Magnetic field. Okay.
Magnetic field.
H is the magnetic field, okay? H is what you create with the current. You remember, if you have Maxwell equations, remember, if you have a wire, you can determine that there is a magnetic field in the distance r, blah, blah, blah. You know how to calculate it. You know that the integral of H on a closed loop is the current which flows through there. Okay.
And this is Ampere's law, right? That you described?
Maybe it falls under Ampere's law, but again, I don't remember the name. So.
Because then there's also the next part where the electric field is created on the capacitor.
Oh, okay. No. Let's stick with.
Okay, so just the current flowing through the inductor.
Current will create. So if you have a wire like that, you create a magnetic field. If you wind it like this, again, the same. Like because if you have a wire like this, it will create a magnetic field like this. If you bend it down, it will create like this, and therefore it will enter in this direction. Now this is very bad, but I hope you understood. Like if you have this wire here, it will create a magnetic field, which is like this. If you bend it like this, it will have all the magnetic field in this direction. Okay, so it will all generate some magnetic field like that, and that means that the field enters like that. Very bad explanation, but I probably don't need to repeat because it's all the Maxwell equation we have already seen. Okay. So magnetic field is amperes per meter. It's measured in amperes per meter. That's what is produced by the current. Then this depends on the material. If we are in vacuum, we have 0, 4 pi 10 to the minus 7 ergs per meter. So this is the magnetic flux per unit of surface. Okay. So if you have, if you want the total flux, you have to take the flux density, so how much flux per unit of surface you have, times the surface, and you get the total flux, okay? Okay, so magnetic flux density, magnetic field, and so you have a flux here. Inside here, you have a flux, okay? You have a flux because you have a magnetic field. Inside just imagine that you have solenoid. You inject the current, inside the solenoid you have magnetic field, H. Because of air, you have a B, which is mu0 times H, and then you have the surface, which is the cross-section of the solenoid. So if you multiply B times the surface, you get the flux inside this solenoid, okay? So you inject the current, I, and you get a flux, okay, magnetic flux.
Yes.
Fine. What do you think is the? How do you think is the relationship between a flux and a current? What type of relationship?
Proportional.
Proportional, because if you double the current,
Double the flux.
you know that what
But
is
there would be a saturating point.
not in air.
Really?
In air, no.
Or if there's like an iron core, you could.
If you have an iron
yeah,
core,
yeah.
yes. If you have a ferromagnetic core, then it will arrive to some saturation. But let's keep it with air.
Yeah.
Let's keep that with air. So you know that what is the magnetic field produced by the solenoid? If you have n number of turns.
Oh, okay. But I'm just gonna recall it from my mind.
Okay.
It's n squared. Okay, it could be just n, but I think it's usually
It's
n.
the number of turns.
Multiplied by the area.
If I give you the current.
Oh, I. Divided by d. Or L.
L, the length.
Yeah.
Okay.
What was I?
I don't know.
N squared times A
Nevertheless,
times I.
the most important thing here, don't mess up with your mind.
Sorry.
The most important thing here is that H and I
Are proportional.
are proportional.
Because N and L are constant.
Exactly. And well, in any case, even if they would change, it's not a matter of the relationship between these.
Yeah, they're still the same.
Now,
N could change if
and
you have
even
a
if
variable
you can see it because
inductor.
from the Maxwell, from the equation of Ampere's law, probably it's called, like if the integral of H over a closed loop is equal to the current, it means you double the current, you double the magnetic field. Okay. Then this could have any shape. It could be a straight wire, it could be a solenoid, whatever. But at the end of the day, you double the current, you double the magnetic field. Okay. So the current is proportional to H, which is proportional to B, okay, because we have this
Mu,
constant,
which is a constant.
which is proportional to the flux, because it's just a matter of surface. So the flux is just the flux density times the surface.
Yes.
So, can you write down our magic equation for the inductor?
Which one?
Which makes what type of relationship there is between flux and current. Where's the equation? Ah, here. So before, again, in fact, wait a second. Before, remember, we said that between voltage and charge, there is a proportionality. There is a proportional linear relationship. Now we can do the same
No, it's not
for
charge. It's not charge.
flux and current.
Okay, so,
Remember,
so I first need to identify what's the analogy. Okay, so in a capacitor you have charge, in a magnetic field you have B, flux density.
You have the flux.
Okay, so the flux. So I'm going to say the flux in the inductor is equal to the inductance times I.
Times the current, okay.
Yeah, because the capacitors are voltage components and the inductors are current components.
Everything is flipped.
Yes.
Okay? What was voltage now is current.
Yes. So for a capacitor, let's say the active component is charge, and an inductor, the active component is flux.
Rather than
because
active,
that's like electric flux, right?
Rather than active, I would say state variable, like state. Which defines the state.
Yeah. Could we say that this is electric flux? Charge is electric flux.
It's charge. Let's call it charge. Don't give extra names if not.
But if that's magnetic flux.
Okay, if you want to call it electric flux, but I think if you stick with the original name, it's charge. People, you see, people see the idea of charge. It's a little bit more difficult with the idea of magnetic flux.
Well, charge is between two things. And
not necessarily.
No? Well, in a capacitor.
No, charge can be also like charge here, which generates a magnetic field. And that's it.
And in this case, it's feeding back onto itself.
In this case, you have a flux, which means that you have an area where you have some B going through, and therefore you have a flux.
Okay.
But let's not complicate too much the things. No, that's not a problem.
Oh, do they see that? There.
Okay.
Q is equal to L times I.
The flux is equal to the inductance equal to the current. So as we define the capacitance, remember, capacitance was how much charge you get for unit of voltage that you have at the capacitor, okay? The inductance is how much flux you get per unit of current. So that also, what does it mean? That if you have a bigger inductance, okay, you get more flux for the same unit of current, which means that you have, for instance, not an air core, but there is some iron inside. Let's assume you have a perfectly ideal linear iron which never saturates, or at least you work in a range before getting to saturation. So you get bigger mu, which means you have more flux for the same current, which means that you have a bigger inductance, okay?
Your storage has increased.
Exactly. So again, we can draw down our relationship. In this case, we have current, and we obtain flux. If you remember before, we had a similar one. The analogy was that we have voltage and Q, okay? Now we have flux and current. Again, we can continue this, this analogy, and everything is really the same. Now, maybe take this equation. So we know that phi is equal L, the inductance, times the current, okay? And now, what we did before, when we use Q equals CV?
Oh, we derived each side.
Okay, then do it. Okay. Oh, maybe move. So you derive the flux and you get the derivative of the flux in time. You say that the inductance is constant, you take it out. Otherwise, you would have the derivative of Li. The derivative, you consider constant. L constant, you get out. So derivative of I. Fine. What is the derivative of the flux? If this is the flux which goes inside here. Induction law.
It's the voltage.
It's a voltage. Remember that it should be with the minus. But now let's consider that we know that the voltage it will be with the minus if you consider the proper convention. So let's forget about the minus and let's say that it's a voltage, okay? So remember that the voltage is because otherwise you have infinite energy.
Yeah, it feeds itself.
Okay, so
V.
Voltage is equal to
L di.
Di in dt, okay? So this is going to be our voltage-current relationship for the inductor, okay? So this goes to our bank of equations that we have. Again, let's try to understand the physical meaning. That's induction law.
Inductors resist the change of current.
Yes. So in this case, first of all, previously with the capacitor, we said we get a stream of charge. Remember that we say that I is equal C dV dt. Okay. What was the physical principle? We said if we get some current, it's only because we take out or we put in some charge, and if you put or remove some charge, the capacitor, the voltage change. Here, the physical principle is on an inductor. When do you get a voltage? When the flux change. And when does the flux change in an inductor when you change the current. Okay? So only if you change the current, you inject here or remove, whatever, you change the current, then the magnetic field changes, the flux changes, and that's the only moment when you get
voltage.
When you get the voltage. Of course, you say, yeah, oh, look, now I have the derivative, and I have the current under the derivative, right? So now that's the physical quantity which is going to be limited in its change. Because I cannot have a step of current, right? Because otherwise, that would require infinite voltage, okay? And that's actually what happens in some cases. We'll see later with the transient. Fine. So now let's work now on understanding. No, let's follow all the procedure we had before. Let's go on sine waves, okay? Let's try to go for sine wave. Again, we have our equation on time. Let's try to transform it for sine wave. So let's say that the current again is a sine wave. So draw the current. I will maybe make some space here.
Yeah. In one graph?
If you wish.
Okay, and what's our voltage?
No, the current. You start with the current. The current is
sine wave.
As a sine wave, okay? Okay. And write down the equation, okay? Maybe somewhere here we can erase this. We leave this one. So I, the current as a function of t, will be I then the voltage is what? L, the derivative of the current. So V, the voltage as a function of time, is equal. No, just write voltage equal.
This.
Voltage as a function of time.
Okay, is equal to?
Equal to L, derivative of the current. Okay, if you want to express like
so this mark is for the... You want me to derive it?
Exactly.
Okay, sorry.
Okay. So,
yeah. Yes.
Okay, so
yes, that is it.
Maybe take the omega in front, so you have omega L, which sounds nice. Doesn't change. So, try, now you have a cosine, okay? So now the voltage is cosine. Where is the minimum? Okay.
Sorry. Goes there. There.
Okay. So can you draw down the phasors?
Just take.
Okay, so the current is on the real axis because it's a sine, so at time 0 it is 0, and this is so at like you have, maybe let's use another color. Let's use a purple, no, the orange. So you have a voltage there. Okay. Just call it with a name. Let's call it voltage, V. Okay. Maybe we can even say that they are phasors, okay? Again, the same thing as we did before. So the fact that we go from sine for the current to cosine means that you have a phasor of the voltage, which is J, and the J expresses the fact that from sine we went to cosine. So we have now the voltage before the current, okay?
Yes.
So now you have the voltage which comes first, and then you get the current. So now we have J, which means that we have pi half, the phasor of the voltage comes pi half before. Then omega L, and then the current, which means that this is the impedance of the...
Yeah, that's XL.
XL, okay.
Or
so
ZL.
This is XL,
yes.
and this is
ZL.
ZL, okay.
And just for the record, this pi over 2 is signifying that it's starting at 90 degrees, not that the amplitude is
Of course. The amplitude will be ZL times I, okay?
Yeah.
So we have a shift of pi half. And again, we got to the point where we derived what we typically see in sine waves, starting from where? From the very basic of the physics of how the inductor is, of what an inductor is, okay?
Yes.
And what is the analogy we can see now? It's not so easy to get.
Nah, you said it once before. It's a spinning wheel.
Spinning wheel?
Yeah, you can imagine that.
Oh yes. You can see it somehow as a
it's a bicycle wheel.
Bicycle wheel, where you first give the tension, meaning that the tension is your force, the tension you put on the wheel, which is in this analogy compared to the voltage, and then after that gets the current, which is the kick that you get if you try to stop it. Like you know when you were a kid and you were cleaning your bicycle upside down, and you were putting upside down, then you start with to move it, and then when you try to stop it, it tries to kick you. Why? Because first you get the voltage, you get some energy, then the current gets after you, okay? And the current is the kick, in this analogy, is the kick that you get if you try to, after spinning your bicycle upside down, you try to stop it and say, how can you think I'm going to stop? I have to give the energy somewhere, and they give it the kick, okay?
And would the inductance in this analogy be the mass of that wheel?
Probably, yeah. I think so. Because that's if it had no mass, it wouldn't have any energy to give anywhere. So the bigger is the mass, the bigger is the kick that you get if you are spinning at the spin.
Now, what you also said was that the inertia is, or let's say the energy is put in first. So in this case, we got to get the wheel spinning. So in the inductor, it means that how would I explain this? What I saw.
It means that
the capacitor, the inertia is experienced at the end. With an inductor, the inertia is experienced at the beginning.
But it depends what you define with beginning, because they both
steady states are at 0.
Yes, but they both have some inertia. if this is the thing you mean with inertia, because in the capacitor, there was some inertia by the fact that you cannot change the charge instantaneously. Okay, because there is a charge there, but we saw that we cannot change the charge in 0 time. There is some inertia to change the capacitor. And again, when you discharge it, it cannot happen in 0 time. Okay, so every transfer of energy requires some times. So there is always some inertia of the system. With the capacitor, it was the charge which couldn't change instantaneously, and therefore also the voltage which couldn't change instantaneously.
Okay.
In this case, it's the magnetic flux. Okay. In fact, you can, if you want, you can again make the same exercise where you take the voltage, the current. I will, if you forgive me, cancel this, and you say, okay, here. I don't know if you can see. Okay, yeah, it's visible. Here is positive, so voltage and current are both positive. Then here you have positive current and negative voltage. Negative, positive, and negative again. So if this is the power is positive, and negative again. This exchange of energy as we did with the capacitor, okay? Now let's watch this energy in our graph which defines the state of the inductor, which is exactly the same thing we did with the capacitor, if you remember about that. In the capacitor, we had this graph where we had Q, V, and we said that this was the energy of if you
in the capacitor.
In the capacitor, if you move from 0 to Q and from 0 to voltage, then this is all the energy that you put inside, okay? What about the flux?
Magnetic flux?
Yeah. So draw the same relationship, but so now we know that the inductive flux is the L times the inductance. We have a linear relationship. So we move the current from 0 to V, okay? Okay.
Yeah?
Yes. All this area is all the energy that we put inside the inductor, okay? Maybe show a little bit. I'm not sure if they can see. So, previously we said that the voltage cannot change instantaneously in the capacitor because it would mean that you have an infinite, an exchange of energy which happens in no time. Instantaneously. Here is the same thing. If we go from our initial point here to our final point here of the characteristic, so the current at the beginning is 0. The current at the end is some whatever value. And the flux changes because it's proportional to the current. Then we cannot change the current instantaneously. Okay?
Yes.
So that's what you were saying probably before, if I don't...
yes, you're right.
That now the inductor resists to the change of current. So, and we know it because we know that the voltage is L di in dt. So again, if you try to change the current instantaneously, then you would require infinite voltage because you have a derivative of the current which would be infinite, quote mark for the mathematicians. But this would, if you have a step of current, if you have a current which changes in time as a step, this would mean that the voltage would be infinite, which is not possible, okay? So, again, we have this, maybe we can prove this is true. The analogy is clear, but just to be 100% like complete in our discussion.
Well, we're going to get the energy of the inductor.
Yes.
Right? Yes.
Let's get the energy of an inductor. Okay. Again, we know that the voltage is what?
Oh, the amount of work done over a distance.
Over the distance.
Over a charge.
4 units of charge, okay?
Yes.
So, of course, over a distance from point I to... Okay, the voltage between 2 points, I and B. Okay, so the voltage is equal to the elementary work over the elementary charge, okay? For moving from point A to B, okay? We don't stay here, we don't repeat it from A to B, whatever. Which means that...
DW.
And we know, yes, dV is equal V
dq.
dq. Okay, now we know that because of the voltage is the work that you make to move some charge from one point to another, we know that the power is given by voltage times current,
yes.
okay? So we know that the power is voltage times current. Why? Because the voltage is the elementary work per unit of charge. The current is the Q dt. Okay? So this means that you have a power. Okay? The definition of power is how much work per unit in time. Okay?
Yes.
So if you want the energy,
we integrate.
The energy is VI dt, okay? You take the power and you have the time, okay? So the elementary work will be the power times the elementary time. So far, so good?
Yes.
Now, what is V dt?
It's the current.
In an inductor, the voltage is
L.
The dt, but if you want to watch it with the flux, induction law.
Oh, -1 multiplied by the derivative.
Let's forget about the moment of the negative.
The derivative of the magnetic flux.
Okay.
With respect to time.
Okay.
Oh, so it's going to be the magnetic flux.
So
the derivative of the magnetic flux.
dF is equal to V dt, okay?
Yes.
So here I have.
So dW is equal to I.
V dt is
d phi.
d phi.
There you go.
dt. Now there's something wrong.
Oh, there's I missing.
Ah, hi.
And dt shouldn't be there because we substituted.
Oh, correct.
Yeah.
Sorry. Okay.
Now we integrate it.
Now, thank you very much for the correction. Now, if we go here, let's again draw back our state graph. So this is the flux, and this is the current, okay? And we know that C equal Li.
Yeah.
Now, let's take a point of this relationship, of this graph. And let's take this elementary slice. Let's say this is dphi, so very, very small slice at a given point of the current, okay? So what is this? This elementary small slice is dphi times current.
Yeah.
Which is the elementary work.
Ah.
Okay? And again, what you're going to do, if you want the total work that you get, the total energy that you put in an inductor when you insert, when you move from a current which is 0 to a current which is capital I, which means to a flux from 0 to a flux phi, you have to take the total, you have to calculate the total energy as the integral of from 0 to the final flux phi, so from here to here, of
I
what?
d phi.
The elementary work that you make in this in this journey from this point to point. So all these little slices,
Yes.
which will be the integral from 0 to phi of
I d phi.
I d phi. Okay. And again, then you calculate, blah, blah, it's the same that you did before. Okay? So maybe I will sit down here so I can draw it better.
That works.
So what does it mean? You know that the flux is L times I, right? So I will be
Phi
flux
over I.
Over L, okay?
L, yeah, excuse me. Yes.
Did I make any mistake?
No, you did not.
Okay. So we integrate this over
Is phi squared.
over from 0 to phi, but I is a function of phi.
Yeah.
Okay, so I as a function of phi is phi divided by L. Okay, so we should put I of phi because it's a function of phi and it changes when we integrate over phi. Okay.
Okay, so it's going to be 1 over L times.
So the total work
1
will
over.
be 1 over L, the integral from 0 to phi of
phi.
Phi the phi.
Okay.
So which means it's 1 over L
times 1 over 2.
1 over 2.
Of phi squared.
Phi squared. Okay. Then you know that.
And this phi squared we can put back to current.
Okay, so we can put the flux instead of the current.
Yes.
So we get 1 over L,
and
2
then,
over L, let's say.
Yes, and then L squared, I squared. Cancel out the L. 1 over 2, I squared. L I squared.
I squared, okay.
Yes.
Let's put.
Very nice.
Okay.
And that's also the opposite of the capacitor.
And remember, 1/2 CV was the energy of the capacitor. Now, again, it's everything. And
or complementary.
Complementary, let's say, yeah. And again, it's all this area, which is the area of the triangle. Okay. Fine. This is, I don't know why, but sometimes students have some difficulties to understand that there is some energy also in the inductor.
Yeah, for sure.
Yeah, but I don't know why. I don't.
Because they can't fathom it.
I don't know. When they see the capacitor, they say, "Okay, fine. I charge the capacitor."
Because they can see it's in between two things. That's why.
Okay.
An inductor, it's like, where is it?
So where is the energy? But as a matter of fact, you can get energy in and get energy out. And you see it, well, mathematically you see it here. There is some power going inside. There is some power getting outside. Maybe if you watch the transient, it's going to be easier to see that there is some energy that you... There's this idea that you can charge up an inductor.
Oh, yeah, for sure you can.
Yeah, but probably that, I don't know why, I'm just telling you my experience, that many students think that they can charge a capacitor because the idea of charging is associated to the idea of capacitor. But also the inductor has some energy, and there is some energy also in the magnetic flux itself, and that's it, that's there.
Well, maybe...
Phi square.
Maybe if they viewed the the inductor as a transformer.
Or which
And
transfer, which can the magnetic flux can transfer energy from one
Side to another.
from one coil to another coil. Yeah, that's an idea.
Because there you have the two components that are coupled.
Well, they are coupled, and you, with the current, you create a magnetic flux, which then is transferring energy, like contactless, let's say, to the other.
Exactly, yeah, exactly.
So
Except the transformer is shorted on the one side, and that gives the inductance.
The best thing, I think, is to see what happens in the transient.
For sure.
Because let's maybe we do later the nice precise derivation of how the transient is. Let's say that we have an inductor which is already at steady state. Okay. So let's say that you have our inductor. It's already at steady state. So there is some current running. Okay.
Well, yeah. Now that it's in steady state, it's basically a short.
Okay, yes. So you have our source, you have our inductor. So the current is already the maximum current. So here the current of the resistor is the same current of the inductor. V, you know that L dE dt, which means that if the current already arrived to its steady state, it means that it's constant. So you have some current which circulates. It means that here the voltage is 0 because the derivative of the current
is constant.
Is 0. So there is some current there.
And that's
and that the current will be after, if we are in steady state,
Vs over R.
Yes, over R, because if this voltage is 0, the voltage on the resistance is equal to the voltage of the source, okay? So now we have this current which circulates. And then you open the switch.
Yeah.
Now, what happens? Because I kept saying, okay, the current is under the derivative, so you cannot have a step of current because it would need infinite voltage, okay? Because we would have infinite derivative of current. So you cannot do it. And you tell me, haha, look, now I'm going to do it. I open it and I create a step because one moment before I had, 1 ampere running and now I open it. So in 0 time, you see that I'm going to
have an instant spike because the derivative of I is now infinity.
Which means that the voltage is?
Infinity.
And which means that the current will
spark.
There will be a spark.
Yeah, yeah.
Exactly. There is a spark because you try to impose infinite derivative of current, and the circuit responds with an infinite voltage. So here, between this point of the switch, there will be a very large voltage as a result of your attempt to break the current. And that this voltage is so large that it can break the air.
Yes.
And find a way for the current to flow. Mm-hmm. Because as a matter of fact, you're not going to break it anyhow. Because the current will find its way to flow. The spark is just a way the system has to still impose that you cannot have infinite derivative here.
Yeah.
You try to open it, but the system say, no way, I'm not gonna let you have a step of current. I'm still let the current flow, even if you try to open it. And how do I do it? Just creating a channel for me to flow, even if you open the switch. And it does so by creating a channel in the air and still continue to flow, even if you open the circuit. So that's why you should never open a circuit like that, because it creates a spark.
Yeah, there should be a shunt somewhere or a diode.
Or whatever, yeah. If there is some current, then it must have some way to flow through. Again, an analogy in the physics world would be like that you are running, So you have some kinetic energy. Okay, so you're running, and you are running at, I don't know, some speed. And then you arrive, like you're here, you're running, and then suddenly, boom, like in the comics that there is some, like, boom. And then you want to stop immediately there. You're not going to do it. You cannot just suddenly stop. You're going to fall down, and you die. Hopefully not. But you cannot just expect to run, and then suddenly stop there instantaneously. There's no way. Here's the same. You have a current which is circulating, running, and then you want to suddenly stop it. No, it will continue and it fall down in the pit and whatever.
Yeah, there's inertia.
It's inertia, so you cannot just stop this. So it's still always the same principle. So you have some energy, and here maybe you can see that there is some energy because there is some current there, and you can see that if you try to open it, the energy will try the way to still flow, okay? Because there is some energy, it has to discharge. It cannot just magically disappear in nothing, okay? Fine. So
it won't be infinite voltage. It will be that voltage will be limited by the amount of energy in the inductor.
What?
So if you plot the voltage that you will see across the inductor.
Okay, let's make maybe the plots of current and voltage.
Okay.
As now, this was just to show the
the
idea of energy, the idea that you have some energy in the inductor. Okay.
This is also in your class why you stressed that when you are using current transformer.
Of course, when you have current transformer,
you should have a shunt there.
You have always to close it before removing the ammeter, because otherwise you have the current in the secondary which goes through the ammeter, which is a short. Okay, so you have your circuit where you want to measure the current. You have here your ammeter. Now the ammeter is a short circuit, okay? So you can ideally see it as a short circuit. So there is some current here which circulates. And it does circulate, and you cannot just think that you can stop a current, an inductive current basically, by opening, because otherwise, boom, spark.
Yeah.
So that's why you always have an ammeter, but always available a shunt here that you should close before removing an ammeter so that the current will circulate.
But in the lab, they soldered resistors there, and we weren't measuring the current, we were measuring the resistance.
Oh, yeah, no, then of course, but yes.
Which is still current, but you're using the VIR.
Well, the reason why they sold the resistor is because people typically tend to forget, even if you put the shunt there, and then, sorry, we measured the voltage there, okay. Again, just to be 100% safe.
And it's a nice way to measure current.
Sorry?
I don't know, I just like the way to measure current like this, because it's not invasive on the circuit. Because usually this is not a coil, it's just one wire, so you'll have...
But, well, the main advantage is that there is galvanic insulation.
Yes.
Because you always affect the circuit, even if you have some, or just one, the fact that there's only one wire, well, sometimes it's just comfortable because you just clamp it.
Yeah.
So from the practical point of view, from the electrical point of view, still is affecting because there is some energy which goes from here to here.
Yeah, you add inductance to that wire.
Sorry?
When you put the current clamp there, that wire has now more inductance because there's a transformer around.
It's a transformer. It's always a transformer, so it's taking some energy from the circuit.
But that's true, right?
There's
more inductance on that wire now.
Mutual inductance, probably. I don't know, but always try to see the point from the energetic point of view, which, in my opinion, is always the best because it shows you the state of the system. when something is screwed up is because you take energy out of that or you put energy, okay? So you change the energy of the system. And that's what is changing in one way or another the state of the system. So in this case, you have some energy because you have some energy, you have some current going here, you have a resistor. Even if you have a direct and ammeter, you still have some current which is flowing through an ammeter, it has some resistance, and therefore it's absorbing some small current, some small power. And this power doesn't come out of nowhere. It comes from a circuit. So
for very small currents, it might not be good. For very small currents, you might affect the circuit.
Oh, this is used when you have a large current, of course.
And you don't want to touch that circuit.
And you want to touch. Yeah. So it's always invasive. It's always taking some amount of energy from the circuit. The advantage, well, one advantage is, as you said, is that sometimes you just go there, you clamp, and pops your ankle. You don't have to unscrew, if there is some wire which runs there in some installation, you don't have to remove the wire and blah, blah, blah. So it's like, from the practical point of view, is advanced. Yes. But one of the second advantages is that you don't have galvanic, that you have galvanic installation. So there is no direct contact between the two circuits, which if you have a large current, is always a big plus because you don't want to, if you want, like, I don't know, you have a solar system, you want to measure the current to monitor the productions whatsoever. So you don't, and maybe you connect these meters to some electronics which
noisy.
Calculate, no, but mainly some like low voltage electronic which calculates, and you don't want to send large currents through that board, which can create all this sort of
interference,
mess and
heat,
danger mainly.
And
if something goes wrong.
Usually, like a shunt resistor is used besides this. So if you're not using this,
you can use a shunt resistor if the current is
moderately low.
Moderate low, or if you're extremely poor. And no, okay, I won't enter into details of things that I know, but I cannot mention. Now, enough chit-chat about these things. Let's watch the
currents and the voltages.
The currents and the voltage there. So let's erase everything, that we need some space now. Okay, so let's say that you have, again, our source.
Yes, source.
Switch. Inductor. Write down the equations.
Yeah, I was trying to do.
Okay. This means that
it resists the change in current.
Okay, so the current at the beginning is 0.
Oh, sorry.
Okay, so let's say that you have.
Oh, fuck, it's done. Okay.
Here's the current in the inductor, which is the only current, by the way. Here, the switch is open, so the current must be 0. And here also must be 0, okay?
Okay. So
then,
okay, and let's okay, here's 0, and here is minus infinity, and then here's our transient beginning. So we are somewhere here. Okay.
What is that?
That's the current flowing through it because.
Oh no.
It's not charged up. It's going to charge. Oh, excuse me.
It's 0. It's open. It has been there since the beginning of the eternity.
Yeah. So it's going to.
No, but let's. Okay, we have current and voltage. Okay, let's draw here the voltage.
Yes.
Now the voltage at the beginning is
0.
Let's watch this circuit, okay?
Yeah, it's open.
Okay,
so it's 0.
Okay. Before that, 0, fine. Okay.
Yes.
You can do it with the red if you wish. Okay, let's say that's 0. Then when it closes, let's say that we close the circuit. What happens to the voltage? Look at this circuit. You have Vs, you have VR, and you have VL. How much is VR? Formula, Ohm's law.
It's,
Ohm's law.
wait. No, you're moving too fast. Just give me a second.
Yeah, sure. Just watch this.
It's going to be IR.
IR, okay. And how much is I?
It
cannot move instantaneously.
It's 0.
It's 0 at the beginning. T0.
Yeah. Exactly.
So this current is 0 because you cannot move instantaneously by a step the current. So if it has been, if the current for t equals 0 is 0, also for t equal to 0, let's put it here.
Okay.
Okay. So VR at t0 is equal to 0, right?
So now this is Vs.
So therefore, all the voltage Vs will be left on the inductor, okay? So, boom, okay? The voltage now can change in a step because it's the current which is forced.
Yeah, it's complementary to the capacitor.
Okay. Then, okay, we start pumping energy in the inductor. And you remember that pumping energy in the inductor means that in the graph where you have flux and current, you mean that from here you climb up this ladder and you add energy, okay?
And so it saturates.
So the current increases until it arrives to the maximum, okay?
But let's draw the disconnection as well.
Okay.
And then this is going to decrease.
It's going to decrease. Why? Because
it charges up.
The voltage.
And then the resistance of this lowers.
Resistance in quote marks. The voltage is the inductance times the derivative.
And the derivative becomes 0, so the voltage becomes 0.
So here you have large derivative of current in time, and therefore you have large voltage. Here you have small derivative of current in time, and therefore you have low
voltage,
okay? So as you inject current into the inductor, as you rather than inject current, I say rather inject energy. So you increase the current because you give energy to the inductor. So it starts from 0, but then it starts circulating. And as the current circulates, then the voltage drops because the derivative is getting smaller and smaller until you arrive to the steady state where, in this case, the voltage will be 0 for after a long time. So as time goes to infinity, you get voltage 0. But this means that if the voltage is 0 here, the current at steady states will be, let's call it steady state current.
V over R.
Vs over R. Okay, this voltage, because this voltage is 0.
Yeah.
So this voltage will be all on this resistor because there won't be any voltage here. Therefore, the final value of the voltage here will be
V over R.
Vs over R. Okay.
Okay.
Now,
I'm going to wipe this one out. I'm just going to...
You don't like it?
No, I do. But let's put it here. And then maybe...
because you want to draw
yeah,
the discharge.
I want to extend it.
Oh, not very straight.
Okay.
Let's make it straight.
Nice.
Okay.
Okay.
Now, what happens if magically, at some point, we decided that instead of having this circuit, we connect it,
We disconnect it.
disconnect it from the main circuit,
After infinity.
and we connect it here, okay? Now, the current cannot be instantaneously changed. So the current at the beginning
0. I mean,
No.
it's constant.
is still the same value. Let's say that we have, I don't know, 5 volts, and we have 100 ohms. You have 5 divided by 100, okay? Which is 50 milliamps, correct?
Yeah.
Okay. So we have 50 milliamps which run in this circuit. Then,
Oh, there's another resistor. Oh my god, I didn't see it.
suddenly, I stop the current to flowing in this main resistor, in this main circuit, and I turn it down on this circuit. Okay? So the current will have the same sign, will continue to flow in this direction, but now the voltage is not 0 anymore, because the current will flow through R2. So automatically, you create
A voltage on R2.
voltage on R2, and this voltage on R2 will be the current of the
I
inductors times R2, okay? So it means that now, then the current will circulate, okay? Circulate, until it will be all dissipated on this, and therefore it will go back to 0.
Yes.
Okay? So the current now will go down. And the voltage that you create,
The voltage goes negative. Because when discharges, the polarity changes.
wait, but now you measure the voltage in this direction, right?
Oh, in the opposite direction. Okay, so then it will shoot up.
Okay, so now the current is circulating and you create a voltage in this direction. If you consider positive the voltage in this direction, so when the current was entering this direction, we consider voltage like this, positive, and then we have again a current which is positive in that direction. So you have another.
Okay, so we need to we change the way we
It's
measure.
different the value.
No, R2 is different, but previously this voltage was going down. Now that voltage is pointing up. Because when it was going like this, right? Right?
Wait. Here you have a current which enters here, right?
Yeah, and the voltage
And the voltage
pointing up.
is here.
Okay.
So the current enters in this direction and it flows in this direction, okay? But then, okay, the point is not the voltage, the point is the current. The current, in fact, doesn't rotate in this direction, but it rotates in this direction, okay? So the error was here. Okay, because here you have...
Yes, I see it.
You have a current which goes in this direction. And the current cannot be changed instantaneously. So when I connect this to a load, the current will continue to rotate in this direction, which means that the current will continue to work to rotate in this direction, okay? And not in this direction as I did before.
Okay.
So the mistake was that I instantaneously changed the direction of the current, which is not possible, okay? So the current rotates like that, which means that the voltage on the resistor, it will be like this, which means that if you consider positive the voltage in this direction, the voltage will be reversed.
So now it's going to go instantly down and up. So I would...
Which, yeah, you can have a different value. Which is something that you see it also here because, well, here the times are more or less the same, so I expect starting from the same value. But here, you see, you know that V is L d in dt. So here, the derivative of current in time is positive. So the voltage must be positive, correct? Here, the derivative of
it's negative.
The derivative of the current in time is negative, correct? Therefore, the voltage
is negative.
Is negative, okay?
But would this voltage not be like 10 or 100 times larger?
It depends on the resistor. Let's say that you have 1 ampere running. If you put one resistor here, you get 1 ampere times that resistor. If you put another, you get the voltage. The current cannot be changed. The current is always here, let's say, 1 ampere. The value of the voltage that you find, it depends on the current.
Oh, that's why if it's open, it's 1,000 because R is 0.
Sorry?
If you open it with no resistor, you'll get a spark because the voltage goes to infinity.
To infinity, okay.
That's why, okay.
Now, and if you close it with the short circuit, it will run forever because there is no transfer of energies.
It will burn
it
up.
must dissipate there it needs a resistor to dissipate this energy. Otherwise, there is no net transfer of energy from the inductor to the resistor.
That's why some diodes have a resistor to limit the impact of the current going through the diode. Because you'll have a flyback diode on inductors.
Oh,
and if there's
you mean also like in the transistor that you get to get back the current? Okay.
Yes. So there's sometimes a current limiting resistor there in case there's a lot of energy in that resistor, and if you're switching that inductor really fast.
Okay. Of course, then you want to, because circuits try to change very fast. Okay, to very fast the quantities, but then you have to work with physics that they want to avoid big traumas to the circuit, to components.
That ultimately reduces life.
You want things to change fast in your circuit. In digital circuits, you always want things to change fast, but then you have to deal with the reality of the physics, that you cannot change as fast as you want. That's why even when you get to these very fast circuits, then they are never squared, because there is always some transit.
Capacitance.
What I wanted to say, I forgot. One more thing. Now, what about tau? Again, we have some exponential, where you have exponential of like this charging or discharging time, where you have exponential of minus t over tau. Now, this tau is L over R, okay?
Yeah. Because
what happens if we have bigger L?
Well, your time constant increases because there's more energy needed to energize the inductor.
So if you have, you know that the energy, how much was it? The total energy?
Just give me a second. Half L I squared.
Okay. So the bigger is L,
The more energy
the more energy
needed
needs
to energize.
exactly. Charge is a word that
Energize.
to energize. Okay, or okay, fine. Let's say charge, whatever.
No, energize.
So it needs more time, and therefore the process is slower.
Do you think Germans run into these like strange ways of calling these things? Because like the German language is like so like compoundly that
I'm not really sure it's a good idea to say things about Germans
well,
live
they're
on.
great at science. So.
No, but about this idea that they want to make their own language, you know.
Not their own language, is that like you can just create words.
That you can plug together all the words. Okay.
And then it makes sense.
Sorry, I understood that you were making fun of German language.
No, not at all. Okay. Because like they're the best in science, and I'm thinking maybe because their language is so like dynamic.
No.
No?
In order to be best in science, it's a matter of money. Just the money.
Really?
It's like...
No, I don't know.
No, yes. Come on, watch.
Okay, America.
Watch how many Nobel Prizes were won by Japanese people. A lot.
Many. Really?
Japanese people win a lot of. Like I have this periodic table of the elements downstairs, where there are all these Japanese people who won Nobel Prize only for chemistry and so on. And the language, Japanese language, is nothing even remotely useful to describe science. Not at all. It's not precise. It has a lot of English terms because the lack of Japanese terms for basically everything which is technical. If you watch a technical book in Japanese, it's mainly written in katakana because there are all these terms which are taken from English. Because even the chemical elements were taken from German. Most of the chemical elements are from German because there was a German guy going there in the 19th century to teach chemistry. So he was teaching all the names of the elements from German.
Okay.
So because before that they didn't have any knowledge of chemistry. And the Japanese language is not good for science, and still they are very good in science, even if the method they use is not so good, because they simply invest a lot of money. You put a lot of money inside and you spend them well, hopefully. You put a lot of money to attract people from abroad. You get the best. You offer most of money, you get the best.
Okay. So in the 1800s, Germany was pushing a lot of money into science.
I'm not sure in that time, but that is a different time, because at that time it was easier to have results even without a lot of investments.
Really?
Yes, because when you were making these experiments, you, a couple of other people in the laboratory, and the money you needed to create apparatus was not that much. It was really based on ideas at that time. After the Second World War, then the era of experiments where you need a lot of money began, because you start a new project, the big projects, where you have hundreds of people working together, where you really need expensive apparatus. And then it's a period where if you don't have the money, you don't do much. So nowadays it's really a matter of money for apparatus and money to attract other people. At that time, it was not even so common to change places. Now, go there, go here to work.
Yeah, it's very
that time, people used to do it, of course, but not so often as now. So. Okay, so we were talking about...
Shift maybe 2 centimeters more. Okay, so back off the tangent, we energize the inductor.
Okay, so if you have a large inductance, it means it takes longer to energize, because you have to put more energy inside the inductor. What about R? If we have a bigger inductor, we have a larger energy. So we need more time to charge it up. So it means that tau is bigger, okay? Because we need more time to give that energy, okay? What happens if we have a resistance which is smaller, okay? smaller resistance, tau gets larger, or bigger resistance, tau gets smaller. Let's watch what happens when you charge it up, okay? Let's see the process of charging. What is the final value of the current that you achieve?
R. It's determined by R in the source.
So the current at steady state, you remember, is Vs divided by R, correct?
Yes.
Because at the end, steady state, the voltage here is 0, so you have voltage divided by current. Now, if you have a bigger resistance, for instance,
the current is limited.
The current is smaller, so you have low energy. So if you have bigger resistance, you have a smaller current in steady state, correct? Which means that the total energy for a given inductance, because the inductance now doesn't change. Now, if you have a smaller steady state, the energy at the end of the charging or the energizing process is going to be smaller, okay? So you have the same inductance, you have a smaller current, and therefore you have less energy to put in. So at the end, it means that it's correct, it takes smaller time to energize. So that's why for bigger resistance, the time for charging is shorter because tau is lower, okay?
Faster, yeah.
And of course, then vice versa. If you have a smaller resistance, then you have the final current is going to be larger, so more energy, so it needs that is going to arrive there later, okay? Mm-hmm. So this was for basically everything for the inductor. Yeah. As you see, basically it's basically the same that of the capacitor.
Yeah, complementary.
Complementary. The role of the voltage is taken by the current. The role of the charge is taken by the magnetic flux. And, well, in this case, we saw the magnetic flux in air. As I said, if you want a bigger inductance, you want a bigger flux, okay?
Yeah.
So
you need to put an object in it which can store that flux.
So we can put some ferromagnetic material, but as you already mentioned before, the ferromagnetic material has some nonlinearity. Okay, let's say that you want a bigger flux. So instead of having air where you get μ0 times h, you put there some ferromagnetic material where you have a relative permeability, which is larger than 1, and you get, for the same current, which generates the same magnetic field H, you get a bigger B, therefore a bigger flux, which means that you get, for the same current, bigger flux. Okay, remember. Yes. For the same current, therefore with the same H, you get bigger B, therefore bigger flux, which means that the inductance is bigger. Okay? Mm-hmm. And we know that if you have 1/2 L I square, for the same current, bigger inductance, bigger energy. You know that ferromagnetic material has a magnetization curve, which, if you start from the virgin point, so never been magnetized in his life, at some point it arrives to saturation.
Yes.
Then you return back. You saturate in the opposite direction, and vice versa continues. Okay? Now, if you add a material which is perfectly, ideally, not necessarily linear, but hysteresis-less, you could have saturation, but without hysteresis, so which means that, for instance, you would have your curve behaving like this. get to saturation, returning back. Okay, so you get BS. It's always risky to use BS, but nevertheless. So what happens when you put some current in the inductor? So let's say that now we have our inductor and there is a piece of ferromagnetic material inside. And it has this characteristic. Fine. You give some energy. We saw it before, is this area, when you go there. And then, so this is the moment when it goes up. And then when it goes down, it returns the same energy to the circuit, okay? So there is no energy lost. You put energy inside, you take the energy outside. Unfortunately, the hysteresis loop, there is some hysteresis in this curve of the ferromagnetic material. So we don't have this, this linear behavior, but somehow we have something which behaves like this. So we have, let's say, our BH loop. My drawing skill when it comes to drawing BH loops are really terrible, but forgive me. Now, when I give energy, I give this energy when I'm going up. But when I'm returning back, I'm here. Okay? So the energy that I receive back is only this slice. Okay? I don't know if the drawing is clear.
No, it makes sense, for sure. Yeah, so, because you have a shorter distance to the y-axis.
So maybe I can draw it in two graphs. Okay?
Now where is that loss occurring? Is it heat?
In the transformer, yes. And the ferromagnetic materials, yeah.
It's the heat generated by the particles changing direction.
Oh, it's definitely going to it.
Because
I don't know if... yeah, okay, so yeah, there is some loss in the magnetic domains like that, but I wouldn't enter too much into these details of the energetic of the magnetic domains. But because there's different sources of hysteresis, so it's kind of complicated.
Okay.
So I will redraw these two graphs, maybe like this. Now the point is that I have to do then the same.
Yeah, so they shifted.
Something like that. Okay. So when I go, when I saturate here, I'm going up in this direction. So from here, I have to the saturation state, and the energy is all this, okay? So it's all this area here. When I return back through this path, okay? So I was going up in the curve here on this path, but I return back on this path, which means that the energy that I return back, I get back it is, so I don't have this part of the energy, which is all losses. Okay? All this energy that I get inside the BH loop is losses. And you can see it also from the energetic point of view, because if you multiply B and H, as a unit, you get energy per cube meters, I think. So if you have a large BH loop, you have large losses. If you have a slim BH loop, you have less losses, okay? And that's also what, again, I try to make this drawing nice, but they still look messy to me.
That makes sense.
That's also what misleads somebody when they use these magnets to produce machines like free energy machines. Because if you use a magnet as a source of energy, you are eventually demagnetizing that, okay? So it means that the magnet has some energy which is not free. It's coming from the fact that somewhere it has been magnetized before. So somebody gave some energy to the magnet to be magnetized and produce magnetic flux, or the nature itself. Once upon a time, billions of millions of years ago, it created a magnet, so it gave some energy. But it's not getting out of nowhere, and it's not infinite. Okay, you always have this energy which is getting out from the magnet, because there was a time when the energy was put there in the somewhere in the past,
between 0 and now.
Between 0, because the Big Bang, and now there was a moment where the energy was put into that magnet to create then a magnet with some energy. Okay, so these things they don't see is that the magnet itself is a storage of energy, which arrives from somewhere, and if you take it out, then eventually you demagnetize. Okay.
Yes.
Okay. I think it's pretty much. Oh no, we can talk now that we know about this.
Yes.
These inductors.
Yes.
We can see one of the most common use of capacitor. Well, as you probably got very well, the voltage, you say, the capacitor
resists changes in voltage.
Okay, so the capacitor resists changes in voltage because we know now have that this equation where the voltage is under the derivative. And so this is for the capacitor. For the inductor,
it resists changes in current.
So
it's L.
The I in the T. So for the inductor, resists changes in current. So how do you use the inductors? Often in circuits, if you want to smooth out some current, you just put an inductor. Okay?
Current ripple.
For the capacitor, you put them to smooth out the voltage. So if you have a circuit and you want to connect whatever, there's something powering up some electronic, okay? So you have a sort of voltage, blah, blah, blah. And maybe this device absorbs some high frequency, because maybe here you have a source of voltage which is very nice, flat and smooth, okay?
Yes, yes.
But here, this device absorbs some high frequency.
Yeah, a bunch of things switching inside.
And then here you get some voltage drop here, which is given by the fact that the current will be given also by this frequency. So you have some voltage drop here, and here you get the source of voltage minus this voltage drop, which contains all this harmonic given by the current, okay? But you want this current, this voltage here, to be nice and clean and not with all these harmonics given by the circuit absorbing all this high frequency, okay? So what you do,
put a capacitor.
Put a capacitor, and we are happy about that, okay? One thing that when I was a young kid I didn't understand was watching these circuits, and I don't know, I was watching like 10 microfarad, then I don't know, 1 microfarad, 1 micro, or I don't know, 100 nano, and so on. And I say, what the hell? Because I had studied, that if you have a parallel capacitor, you sum them up.
Yes.
So you have two capacitors in parallel, the total capacitance here is 100. It's 10.1 microfarad, okay? Correct?
Oh, I
So,
think so
10 microfarad plus 0.1 nanofarad is 101. Which, if you take these capacitors and it's the tolerance. Like, if you take that capacitor, you take one will be 9.9, 110, 1.10.1. So they are not so precise. So if you just take that capacitor itself, probably it will be 10.1. So what's the big deal of adding the 100 nano extra?
the frequency response.
The frequency response.
The quality factor.
Because you don't have a real capacitor. Sorry, you don't have an ideal capacitor.
Yeah.
You have also inductance and some resistance.
Yes, and that defines the quality factor.
So what happens when you have... let's say that we have a model, okay? Let's model out. Let's model out like resistance. Then you have your capacitance, which is what you want. Then you have some inductance. So if you watch the total impedance here, you have R plus
1 over j omega c plus j omega L.
J omega L, okay? So then...
when these frequencies match, it's going to be a purely resistive
Exactly.
component.
So when omega is 1 over square root of LC, correct?
Yeah, I think it's so.
Because you have omega C, okay, yeah, correct. Yeah, you just have to put these two parts equal, then you solve the equation and you get omega 1 over square. Let's do it. Omega L 1 over omega C, which means that omega square is equals to
1 over
LC, so omega is equal square root of 1 over LC.
Yeah.
Okay.
Yeah.
Correct. So these two reactances cancel out and you get only air. So if you plot frequency
impedance
for zero frequency, it's infinite, okay?
Yes.
Because it's a capacitor open.
Let's make this omega prime or something.
Omega prime, okay.
It's going to drop.
So, here is where you get basically
R.
the resistance. So this is the impedance, okay?
Yes. And now these capacitors are going to have different L's.
Of course, because of the construction materials, the packaging, whatsoever, they will have different parameters, different omega 1. So this means that, well, the purpose here is that we want this to be 0 at specific frequency to remove that frequency. Because if it's 0, well, here we have R, but ideally, let's say that there is no resistance. This would be 0, which means that only for that frequency, here you get a short, which means that it cancels, it suppresses that frequency, the voltage at that frequency, because at that frequency, the capacitor behaves like a short circuit. Whereas for 0 frequency, which means that it's not there, it's infinite, okay? So that's the beauty of the capacitor, which behaves selectively as a short circuit for high frequency, suppressing the voltage because it imposes a short circuit there. Then what you do is to have different capacitors, which all together, one or another, will suppress
a band or
a range of frequency. So, okay, maybe I didn't draw them very well. Let's say that ideally, it's kind of, it's not really, but something like that.
But it's closer.
So, if you have different
Q factors,
different capacitors added together in parallel, then you kind of get something like that, okay?
Oh, yes, yes.
Maybe.
So it's not just the capacitance that's being added, it's also the inductances and the resistances.
Yeah, you have to take into account that you have all these. Why? Because here you have basically the capacitor. So generally speaking, if you have only the capacitor, simply you would have going down to 0 without no problem. But you have also the inductor. Okay, so this is the fact that the inductance gets lower and lower as you increase the frequency.
Yes.
But then at some point, so at low frequency, this dominates. Because at low frequency, this is basically a short circuit, but this is large. So this is negligible, very low. This is very big. So at low frequency, this dominates.
Yep.
At large frequency,
that dominates.
At large frequency, this becomes 0, which is what you want. But unfortunately, there's still also the inductance, which spikes up. Okay. So unfortunately, at high frequency, then you have the inductors, which spoils everything up. So if you consider also the capacitor, also the inductor, not only the capacitor, you get this behavior, which effectively tells you, okay, I have only this range of frequency where I effectively suppress, shunt down the voltage. But I want it on a larger range, okay? So what do? Is I add extra virtual short circuits using, or not virtual, selective short circuits.
Yes.
Selective short circuits, also for other frequency here and here, by using multiple capacitors which have different resonance frequencies for different values of resistance and of capacitance and inductors. So I will have another which goes here. So here, this frequency is not suppressed by the first capacitor, but is suppressed by the other capacitors. And that's it. So that's why, if you consider theoretically two capacitors, only capacitors, doesn't make sense. Why would you need to put two capacitors where this is basically negligible compared to this one? Doesn't make any sense. But if you consider that there is also an inductive component, then this capacitor is not like ideal suppressing everything over some frequency, but it has this inductive component which screws everything up. So if you want to suppress also that frequency, you need also that another capacitor to
make it more selective.
So then you make your calculation, blah, 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 both. Okay?
Very nice explanation.